Hello everybody, welcome back to another Algebraic maths video. It's been way too long since I picked up the camera, the phone, and the tripod, but I'm back. Okay, I'm back, and I've been learning. I've been doing some algebraic geometry in the time that I've been off camera. I got a fresh trim, so I looked handsome for a while. But it's been so long that my hair just it doesn't look fresh anymore. But apart from that, not much has occurred. I have been doing a little bit of algebraic geometry learning, so I kind of know what direction I'm going in. I took a little look at Vakil again, so I kind of get like the whole varieties as kind of the whole historical thing, and then schemes as the more modern, the algebraic geometric language type thing, the Grothendieck type language. But I'm still going to be going through algebraic geometry quite slowly, and so I've even taken a step back from varieties, which you would think is kind of like the first topic in algebraic geometry. Because what I'm doing now is I'm going through a book on complex algebraic curves, which basically, so I'm going through like the ultra hyper mega historical route, where you basically go through complex algebraic curves first, studied by Riemann and the like, and then you go to varieties, which I hopefully won't spend too long on. I'll learn some algebraic geometric gadgets, and then hopefully by that time I'll be super motivated, I have a ton of examples and whatever to go straight into schemes and sheaves and all of that cool stuff, sheaf cohomology and all this modern technology in algebraic geometry. So I will eventually end up using Vakil, but that is very far in the future. For now, I take a look at some complex algebraic curves, and since I've already covered quite a lot of algebraic curves, well, not quite a lot, but I've covered a little bit of algebraic curves stuff already on this channel, I won't be, going through the definition of an algebraic curve again, because, I'm just doing the same thing, but instead of over a general field K, I'm going over the complex numbers. However, so today what I'm going to be going through is basically singular points, and the multiplicity of a point on a curve, basically. And, and specifically I'm going to be going through all of this in the field of complex numbers. So I would have done this in general, but I'm going to be going much more slowly, and I'm going to be going really in depth straight on the complex curves, and hopefully that gives me tons of motivation for studying them in general later through Shafarovich and whatever. So basically today I'm going to be going through some properties of algebraic curves, and then next video I'm going to be going through projective stuff, projective means and all of that stuff, and then going through whatever, okay, you'll see. Hopefully I won't keep you in as much suspense about the rest of the series as I have for this particular video, but okay, let me just get into it at this point. So yeah, I guess the place to start would be the definition of a singular point. So I don't even remember if I've covered this already, but I will assume that I haven't. So the definition of a singular point is quite simple. So again, we're working with complex algebraic curves. So if we're given some complex algebraic curve P of xy, then a point AB is singular if the partial derivatives are also equal to 0. So the partial derivative of P with respect to x evaluated at AB is equal to 0, and that's equal to the partial derivative of P evaluated at y. That's not supposed to be a theta, that's a 0. Yeah, okay. Okay, so that's a fairly natural definition to come to, and okay, we can study these singular points, which actually will be studying these singular points in. I've seen the contents of the book they study singular points like all the way at the end of the book, the complex algebraic curves book. So there must be something very interesting about this type of thing. But you know, it just seems like quite a natural definition to me at this point. Forget what I was gonna say. Yeah. But yeah, so that's the definition of a singular point. And oh yeah, I remember what I was gonna say. So of course, you know, an algebraic curve need not have any singular points, and so if an algebraic curve P, so I'll say if P has, and then sing of sum of P equal to the empty set, that is, this set of all singular points is empty, as in there are no singular points. If there are no singular points on this curve P, then it's non-singular. Then P, descriptively named, you know, is non-singular. Okay. So we have this definition in hand, you know, for later, I reckon, is when we're going to be needing that definition, but it's always good to have it in the bank. Okay, so now let's get on to some slightly more interesting stuff, and I believe what's going to be useful when we're looking at projective curves. That is the notion of a homogeneous polynomial. So definition. We have that a polynomial in n variables, p of x1, blah, 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 xn, is homogeneous of degree d if, so we have some polynomial in n variables and it's homogeneous of degree d if we have that p of lambda x1, blah, 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 up until lambda xn is equal to lambda to the d times p of x1, blah, 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 up until xn for all complex numbers lambda. And so an equivalent, and you know, and with this equivalent definition it's easy to spot these things. An equivalent definition is if we have a polynomial of in n variables, that is a sum which looks somewhat like this, so we have r1 plus da 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 up until rn equal to d, and then we have some coefficient a r1 until rn, and then we just have products x r1 until x rn. So for example, what this is really saying is that x to the 5th plus 4xy to the 4th plus x squared y cubed. This is homogeneous of degree 5 because, you know, if we have 5 here and then 1 plus 4 is 5 and then 2 plus 3 is 5. So in each of these different components, I'll call them, the degree adds up to 5, but z to the 7th plus y, for example, that's not homogeneous because 7 is not equal to 1. So that's what this equivalent definition is saying, and that makes it a lot easier to spot these different, whether a polynomial is homogeneous or not. So okay, that's the definition of a homogeneous polynomial. And so we're going to prove an important lemma about these things before we get onto the definition of multiplicity and that good stuff, and then the end of the video, basically. So what's this important lemma? Well, the lemma is that if we have some complex algebraic curve p of xy, homogeneous with of degree d, then p of xy can be factored as a product from I equals 1 to let's say d of alpha I x, so for just some complex numbers alpha, So plus beta I y. So it can be factored as this as these linear factors, you know, with complex coefficients, and this is for some polynomial in two variables, and it's homogeneous of degree d. So I am going to go ahead and prove this lemma actually. It's just a neat little proof, you know. So I might as well do it. So the proof of this is, alright, so let's use this equivalent definition right here to write p of xy is equal to the sum from, say, r equals 1 to d of a r. Sorry, this should be r equals 0 actually, I think. AR times x to the r y to the y to the d minus r. Okay, yeah, this makes sense. Yeah, okay. Because, you know, this is yes, this agrees with this definition here, because if we add these exponents, we're going to get d every time, and this just some, you know, it's just some coefficients, and we can rewrite this as y to the d times the sum from r equals 0 to d of AR times x over y to the r. Right, because then we're just left with y to the negative r, which is just x to the r over y to the r, which is, okay, you get it, okay. And so, now if we let e, let's say e is equal to the biggest number in this set of natural numbers between 0 and d.
Here I misspeak, I mean to say such that e is not equal to 0.
In this set of numbers, then, now this thing right here, this sum right here, is a polynomial of degree e. And it's of a single variable, x over y. And so it can be factored as, so sum from r equals 0, so we're ignoring this y to the d for now. So basically the argument is we take out this thing, so we write it like this because it's homogeneous of degree d, and then we take out this y to the d, we factor this part because now we argue that it's a single variable polynomial of degree e, where e is, you know, the biggest number in this set, which is not equal to 0, and it's of a single variable x over y, and we know that that can be factored already, and so, okay, let's write it out, x over y to r is equal to ae times the product from, let's say, I equals 1 to e now, to e, of x over y minus some gamma I. Right, and now we just multiply everybody by y to the d, and the result follows. Minus gamma I y. I believe it is the correct statement of this. But either way, we multiply this thing right here by. I'm not sure if that y should be there, but it shouldn't matter too much.
Felt wrong and it was wrong. The y should not be there.
I'm just putting it there in case it's... Oh, well, of course, in case it's right, and also if it makes it product to d and not just e. So I'm just going to insert it there. But I will correct myself afterwards if that's wrong. But anyway, once you multiply this thing by y to the d, the result follows. So we'll just give ourselves a little QD. Okay, so we can factor it as such. And recall that. Okay, we'll go on to the other side now. Alright, so let's just say that p of xy, a polynomial in 2 degree, recall that it has a finite Taylor expansion around any point, sum from over all I and j greater than or equal to 0 of, so it's got this finite Taylor series expansion of partial derivative, the I plus j partial derivative p. So we do it I times with respect to x, and then we do it j times with respect to y. And then we evaluate this at a, b. And then we multiply by x minus a to the j, to the I. And we do y minus b to the j. And then we go all over I factorial, j factorial. So we have this of course, this is finite because these things are going to vanish eventually. So this is a finite Taylor series expansion that all, of these algebraic curves, they will enjoy this. I think any polynomial will enjoy this. And so, what's the point of writing it like this? Well, what we're going to study, in fact, is these particular partial derivatives, and that's the idea of multiplicity, which actually feeds in nicely with some pretty elementary notions, but defined in much more generality. And in fact, this isn't as general as it gets because, of course, we don't need to be working with complex algebraic curves. Of course, we can do this in any field, not just the complex numbers. But I'm studying complex algebraic curves to get maximum motivation. So I'm taking this slowly, but I am aware that we can do this in an even more general setting. But I'm going to restrain myself for now. Anyway, so let's study these partial derivatives. We say that I think it's a point. Okay, so AB is of multiplicity M if we have that partial derivative of do the nth partial derivative of p, and we do it with respect to x I times, and we do it with respect to y j times, at AB not equal to 0. So for example, any non-singular point is going to have a multiplicity of 1 because by definition, non-singular point has one of these partial derivatives not equal to 0, and so I feel if I explain it, I'm going to confuse the audience, but hopefully it's clear. If it's not clear, then maybe this notation is a bit confusing to you, but basically what this notation means is, because it was confusing to me at first, and also I plus j is equal to m. The notation, what it means is that you do the partial derivative of this p at x I times. So let's just take the function f of xy equals y to the 4th times e to the x. Then if we do the third partial derivative and then we do it x2 times y, this equal to, so we differentiate with respect to x twice. Of course that does nothing because, yeah, it does nothing because this is just c times e to the x. And then we differentiate with respect to y in order to get 4y cubed times e to the x. right? Because that's just the difference. This is just the partial derivative of this with respect to y. So hopefully with that explanation in hand, it's clear that every single non-singular point has multiplicity 1. So, singular points have a multiplicity of at least 2. And also m is the, and of course this is for all I and j, that, so you know, okay? And m is the smallest number such that this is true. And okay, so this is the definition of multiplicity. So for example, the origin has, I believe the origin has multiplicity 2 with the curve y cubed minus x cubed is equal to 0. In this curve, I believe that the origin has multiplicity 2, for example. And, yeah, you know, multiplicity 2, this is sometimes called a double point. And multiplicity 3, this is sometimes called a triple point, and so on and so forth. And actually, these multiplicities, they have a nice connection with tangent lines. So, in order to tie in why tangent lines and tangent curves or whatever have anything to do with this, we have to use the lemma that we proved right here. So, recall this lemma, alright, recall it, and now note that the following polynomials, so a sum over all I plus j equal to m of the partial derivatives I plus j of p. Actually, we'll use m, yeah, we'll use m. And then we do partial derivative x I times, and we do the partial derivative y j times. At ab times x minus a to the I, y minus b to the j over I factorial j factorial is homogeneous of degree m. That's homogeneous of degree m, and so it can be factored as. So since this is homogeneous of degree m, using the lemma that we proved earlier, it can be factored as products. Let's say, yeah, we have some alpha times x minus a plus beta times y minus b, where we have some complex numbers alpha and beta. And so these lines are called tangent lines to this thing right here. And so for a point of multiplicity 1, that is a non-singular point, there is precisely one tangent line. And for points, so there's one tangent line, and it's defined as being, and it's defined precisely by this thing. So for a non-singular point, we have precisely one tangent line. And for example, if I'm going to give you an example, if we have y squared equals x cubed, that looks something like this. I'll put it in decimals later, and you know, I'll blah blah blah. But it has and it has, at this non-singular point here, it clearly has one tangent line which I cannot draw. But how is that tangent line defined? Well, it's defined as the partial derivative p with respect to x at ab times x minus a plus the partial derivative of p with respect to y at AB times y minus b. So this right here is the tangent for a non-singular point AB. A curve is called ordinary if AB, so AB is a multiplicity M, right? A curve C is called ordinary if it has you know what, this definition, I'm going to write it down, because this is not ordinary right here, so it's a pretty terrible example. An ordinary one is, I forget the equation of it, but it looks something like that. Anyway, curve C is called ordinary if AB has M distinct tangent lines to it. So this is not ordinary, this is ordinary. They both have double points. You get the idea. So basically we use this lemma and then we use these factors to define tangent lines, which, you know, we somehow managed to define tangent lines to complex curves, and I will insert, because, you know, I cannot draw for the life of me, I will insert Desmos things in the appropriate, just before, you know, this outro. I got a little bit riled up at certain points of the video, just to emphasize, you know, the importance of certain things and whatever, and hopefully you enjoyed this this video. Hopefully I will be back for good now, you know, with, like, you know, kind of somewhat consistent upload schedule. Actually, I am going abroad next week, so not next week, sorry, the week after next, and so that might just be full of chess live streams, but before that, hopefully I can get in at least one more video, but realistically I should, you know, assuming I work up the motivation, you know, I had plenty of opportunities to make videos, you know, I just couldn't really, I just, like, at the time, I just, you know, lazing around in my chair, and, you know, the phone, the idea of making a video, just, even though, you know, I probably could have made this video, you know, like, a week after my last, the maths video I made last time. I don't know, the phone just looked unappealing, you know, I didn't want to touch it, but, you know, I'm back, and, you know, hopefully for good. I will try to, not force myself, but, you know, just, I'll try to, like, you know, get off the chair, because making videos is good fun, to be fair, it is good fun, but, you know, sometimes, you know, being lazy is just easier, but, you know, no, no more. I will hopefully be making some more videos, especially as I've taken a really long route. I've chosen myself a really long route, and I'm going to try and build up a bank and ton of examples to use when I'm going into the modern machinery that is Vakil. And so hopefully it pays off, but, you know, the only way it's going to pay off is if I continue making these videos for you and for myself, and I'm waffling at this moment, so I'm just going to say goodbye. So, yeah, okay, goodbye, you know, I'm back.